So here I have a 9-volt battery. Yep, 9-volt battery. If you'll notice, you can see there's a little sign on here that says where the positive end is. And what that positive end is, it doesn't actually mean it's positively charged. What it means is it has a positive voltage. So this is a 9-volt battery. So we can say that that positive end has a voltage of 9 volts. So at that positive end, there's a voltage of 9 volts. At the negative end, it says negative. But really, what it means to be a 9-volt battery is that you have a difference in voltage from one end to the other of 9 volts. So we'll just say that that's 0. We'll say that the positive end is 9 volts. And we get a curve that looks like this. Just make that a little bit brighter so you can see it. Voltage from the positive to the negative just goes down. And you get this nice little slope. Well, what exactly is voltage? We know it's how batteries are rated. But what does that mean? Well, voltage tells you the direction that charges are going to flow. If I were to put a positive charge in my battery, recall that we define current as the flow of positive charge, even though it might actually be the negative charges that are moving. But you can imagine voltage is kind of like a hill for positive charges. If I have a hill and I put a ball on it, the ball is going to roll down. If I have a positive charge and I put it on a voltage hill, the positive charge is going to roll down that voltage hill. Now, electricity is a little bit more complicated than gravity is. Gravity will just pull you down the hill. Doesn't matter what charge you are. Voltage is a little bit different because we have to be concerned with whether or not we have a positive or a negative charge. So if positive charges are being pushed away from this end and toward the negative charges are actually being pushed in the opposite direction, which means negative charges actually go uphill in voltage. So what we can say is that positive charges roll down voltage hills. Negative charges go up in voltage or roll up voltage hills. Sounds like a nice hipster complex. You can go, let's move up, let's go upscale, move into the voltage hills. I have no idea what that meant. Main point to take home here, positive charges go down in voltage, negative charges go up in voltage. So we said that voltage is like rolling down a hill. So if I have a high voltage and I'm going to a low voltage, positive charge is going to roll down that hill from the positive, the large positive voltage down to a lower value of voltage. So it's like rolling down a hill, and much like rolling down a hill, you're going to lose potential energy. You must have some potential energy up here. That gets converted to kinetic energy as you go down the hill. So that tells us that there must be some type of electrical potential energy. How can we write that? So charges that are moving in some potential, let's say it's a positive charge going down a potential hill, it's going to gain kinetic energy in the same way that a ball rolling down a hill gains kinetic energy. That means it had to have potential energy to begin with. And we can write the voltage, we can actually define the voltage as being the potential energy per unit charge that you have. So this is the electrical potential energy. Potential energy This is the amount of charge that is placed at a particular spot. If I know the potential energy per unit charge, that tells me the potential or voltage of the system. I should say that's another word for voltage is potential. Electric potential. Now do not confuse the words potential for potential energy. So I'm not quite sure why physicists decided this was going to be a good idea. Because you have electric potential energy here. You have this, which is your voltage or potential. But potential and potential energy are different things. Physicists apparently decided to be lazy that day. To keep things pretty simple, I'm going to try to refer to this as voltage for the most part. If I slip up and call it potential, know that I mean this, not the potential energy. But looking at this, we can describe the units of potential or voltage as, well, it's potential energy divided by charge, so it's joules per coulomb. We define that unit to be V, which stands for volts. So when you are looking at the voltage of a battery, voltage between the two terminals of a battery, what that tells you, if I rearrange this, is it tells me how much potential energy you get for a given amount of charge that you place there. So if you place a negative charge, say you place an electron at the negative terminal, it will tell you how much potential energy that electron has. To illustrate the difference between potential and potential energy, I think it's good to have an example. So say you take some birthday party balloons, you rub them on your head, they get statically charged up. Say you do it twice, and then I put one balloon next to the other balloon. Well, it should be clear that this balloon is going to be repelled to the right. It's going to feel some force. Another way to look at that, rather than looking at force, is to say this balloon feels some potential. If it feels some potential, some electric potential, it's going to also have some electric potential energy. And we can figure out, when this thing gets pushed far away, how fast is it going to be moving once it gets very far away. So let's suppose for the minute that it feels a potential of 100 volts. Suppose that the charge on the balloon is 10 to the minus 7 coulombs, which is, when you rub a balloon on your head, that's about how much charge you get on it. Let's say you have a 2-gram balloon, or roughly 2 times 10 to the minus 3 kilograms. Suppose we want to find out how fast that balloon is going to be going away. Well, we can do that. We just need to use conservation of energy. So I'm going to erase my picture here really quick, so that we can do the conservation of energy problem. Okay. So again, you've got your balloon, your charged balloons close to each other. They're both positively charged. That's picture 1. Picture 2, let's say we hold this balloon fixed, but our other balloon starts to move to the right. It gets pushed off to the right. It gets some velocity. V, we'll call this picture 2. We can say that the energy from picture 1 equals the energy from picture 2. So we could say energy 1 equals energy from 2. And there's 2 types of energy in this picture. There's the kinetic energy in picture 1 and the electric potential energy in picture 1. And that has to equal the kinetic energy in picture 2 plus the electric potential energy in picture 2. Well, we can set a few things equal to 0 here, because initially, let's suppose that our balloons are at rest. Well, if that's the case, then they won't have any kinetic energy for picture 1. Similarly, let's suppose that after a while, this balloon gets pushed so far away that it no longer feels the repulsion from balloon number 1. Okay? If it's miles and miles away, the balloon is not going to feel that electrostatic repulsion. So we'll say that the electrostatic energy in picture 2 is insignificant. That doesn't matter. Therefore, what we're saying is that the electrostatic potential energy from picture 1 gets converted to kinetic energy in picture 2. Let's write that down. So the electrostatic potential energy, well, we said that electric potential could be written in terms of the electrostatic potential energy if I take into account the charge. So we can say that this is going to be the charge of the balloon times the voltage that the balloon feels. And that's going to get converted to 1/2 the mass times the velocity squared. Now notice that we have two V's here. Your big V is the voltage felt by the balloon in picture 1. The little v is the velocity that the balloon has in picture 2. Now, we want to figure out how fast we're actually going to be moving, and we can just solve this equation for that. We'll say that V is going to equal 2Q big V divided by the mass, and then I've got to take the square root. And if I look here, I have big V, so I got that. Q I have, and I have the mass. We can just plug in to find our answer here. And if you do that, you should get 10 to the minus 1 meters per second, or roughly 10 centimeters per second. All we did is we used the voltage, and we used the charge on the balloon to figure out how much potential energy it had. That energy got converted to kinetic energy, solve for the velocity, and you can figure out how fast that balloon is going to be traveling. I have here two 1.5 volt batteries, and we can see that they're 1.5 volt batteries because the instrument that I am measuring them with is a multimeter, which can measure voltage. And you can see that the voltage on this first battery is about 1.53 volts. I can try the same thing. I'm just going to disconnect here. You can see that the voltage reading goes away. I'm just going to connect to the second battery. And you see, again, we get about 1.5 volts this time, a little bit smaller, about 1.51 volts. So suppose I disconnect my meter here, and I were to combine these two batteries. Let's say I combine them like this. So I'm going to combine the head of one battery to the tail of the other, so that I'm going to put the batteries together in series. Okay? In series just means one battery right after the other. If I were to measure the voltage of this configuration of the batteries, what voltage would I get? All right, well, let's try it and see. I'm just going to connect positive end of my multimeter to one end and the negative end of my multimeter to the other. And you can see that I get the sum of the two voltages. So each battery individually was about 1.5 volts, a little bit bigger than 1.5 volts. And you can see when I add them in series, one right after the other, you get the combination of the two voltages summed together, you get about a little over 3 volts. So how do batteries in series behave? Well, we're going to draw a couple of pictures. First is a real-world picture. I take two batteries, I put them end to end. This is what it looks like in the real world. Maybe you've got two Duracell or Energizer batteries. Well, in our abstract symbolic world, we can draw our circuit this way. Here we go. Remember, I represent a battery or an electromotive force in this way. I use a short line and then a long line. And we'll say that the long line represents the positive end of the battery, the short line represents the negative end. And I do that twice. One for each battery. So here's battery 1, here's battery 2. Now, if each of my batteries is a 1.5 volt battery, what this would mean is that I have a voltage change from here to here of positive 1.5 volts. So we'll say this is point A, this is point B, this is point C. Well, my voltage, if I were to plot it, say this is 3 volts, here's 1.5 volts. Well, up until my battery, so at point A, my voltage is 0. So we're starting off all the way on the bottom here. Well, as I pass my battery 1, your voltage increases. So that means your voltage goes up. It goes up to 1.5 volts. Remember, the battery supplies voltage. Important point, battery supplies voltage, not current. All right, so my voltage stays pretty constant there after the battery, but now I have the second battery. And my voltage is going to go up again. Again, it goes up by 1.5 volts. So now, I started at 0 volts. I go to 1.5 volts. Then I go up another 1.5 volts as I go across my battery. So here I'm at 3 volts. 3 volts everywhere after that. So we can actually color code the voltage at different parts in my circuit. I can say everywhere in region A, you get 0 volts. Here we go. That's 0 volts. Between the two batteries, so in region B, everywhere in here, the voltage everywhere in there is 1.5 volts. Now there's an important point about conductors here. Everywhere in my wire is a conductor. Everywhere in that wire, the potential, the voltage, is the same. For that reason, we call conductors equipotentials, because they have the same potential everywhere. I'm going to erase my real world picture. Stick with my circuit world. This is called an equipotential. So everywhere in the wire between the two batteries, that's at 1.5 volts. Similarly, everywhere on this side in region C, it's going to be at 3 volts. Hopefully that comes off on the video. So everywhere in that wire, it's 3 volts. Why is it 3 volts everywhere in the wire? Because the wire is an equipotential. If I have different circuit elements, if I put a battery in here, then the voltage can change. Batteries bring your voltage up. As we'll show momentarily, resistors will bring your voltage down. Now let's try a different configuration. Suppose I connect my batteries again, but this time I connect them in parallel. If I'm connecting them in parallel, what that means is I am putting the batteries right next to each other so that the wires are connected in such a way that the red wire goes to the red wire, so the two positive ends of the battery are connected, and the two negative ends of the battery are also connected. Generally speaking, you usually try to have the red wires coming out of the positive end and the black wires coming out of the negative end. Let's see what voltage reading I get this time. What voltage would you expect to get if I connect the batteries in parallel like this? All right, let's see what we actually get. Well, we see that unlike the case where the batteries were in series, what we get is a voltage that is just equal to the original voltage we had. It's about 1.5 volts. So why is it that when we connect batteries in parallel, we get the same voltage we started with? So again, I'm going to draw a real-world picture. And what we did in the real world is we took two batteries, like this, and then we connected this part of them, connected the positive end, and we connected the negative end. Well, we can do the same thing in our symbolic circuit world. Symbolic circuits can look like this. Again, I have two batteries, except before I connected the positive end of one battery to the negative end of the other. Now I'm going to connect the two positive ends together, and I'm going to connect the two negative ends together. And you can see now the two batteries are parallel with each other. And I have two different paths I can take because the batteries are in parallel with each other. If I was an electron moving through this circuit, you could go around path 1 or you could go around path 2. But what happens here? Well, again, they're 1.5 volt batteries, which means that the voltage from here to here has got to be 1.5 volts. Well, let's say the voltage just below this battery is 0 volts. Well, that means the voltage everywhere on that side of the battery, everywhere that's connected by a wire, has got to be at 0 volts. Because again, my wires are equipotential. So everything over here has to be 0 volts. There's a change in voltage. Let me draw that in white just to make sure it shows up on camera. There's a change in voltage of 1.5 volts going across that voltmeter, which means I go from 0 volts over here to 1.5 volts over here, which means everything over here has got to be 1.5 volts. Let's see if that's consistent. Well, if it's consistent, I should get a delta V of 1.5 volts here, which is exactly what I get. Because again, I connected two 1.5 volt batteries. So we can see that when we have two batteries in parallel, what we get is not the sum of the voltages as we did in series. We just get individually what the voltage drop across each battery was.